All right, welcome to today's Schubert seminar. We are happy to have Christian Gaetz from Berkeley speaking about combinatorial invariance for the coefficient of Q in Kazhdan-Lusztig polynomials. Please take it away.
Okay, thank you very much for having me speak here. The work I'll be talking about is joint with Grant Barkley and Thomas Lamb, who are both at Michigan. So first, I will tell you what this combinatorial invariance conjecture is. And to do that, I need to tell you what Kazhdan-Lusztig polynomials are. So I imagine a fair amount of this, the Coxeter setup will be familiar to most people in this seminar, but I do want to emphasize that I am working in arbitrary Coxeter groups, so not necessarily crystallographic, not necessarily finite. So a Coxeter system is just a group W with generating set S. All the generators are involutive, and the only other relations are these braid relations. SISJ to some power is the identity. That power is allowed to be any integer bigger than 2 or infinity, which just means that there's no relation between SI and SJ. So again, examples which don't need much introduction in this setting. Dihedral groups, these are always Coxeter groups. Symmetric groups, where the SIs are the adjacent transpositions. The Weil group of any semisimple Lie group, or more generally, Kac-Moody group. Or the automorphism group of any regular polytope, for example. All of these things are always Coxeter groups. Now, I'll say in a couple of slides what exactly these things are, but let me just say so Kazhdan-Lusztig polynomials are these polynomials P, U, V with a single variable Q. They are indexed. U and V are elements of some Coxeter group. And it is so I've written here that they have natural number coefficients, that is non-negative integer coefficients. The fact that the coefficients are non-negative is actually uh, a very deep fact. It won't at all be obvious from the definition that I give. But Kazhdan-Lusztig introduced these in 79, and around this time was one of the beginnings of geometric representation theory, and proving the conjectures that they made were some of the first major results in geometric representation theory. And so there is this family of polynomials sitting at the center of several not obviously related things. So one is that these polynomials encode singularities of Schubert varieties. That is, if W is a crystallographic Coxeter group, so that there is a Lie group G, I can look in G mod B, I can look in Schubert varieties. These polynomials measure the singularities of those Schubert varieties. They also, in the crystallographic case, encode information about representations of the Lie algebra G. So they tell us about extensions of simple and Verma modules. And lastly, for any W, they allow us to define the canonical or Kazhdan-Lusztig basis of the Hecke algebra, which also gives bases in its irreducible representations. Okay. So in order to define them, I need to tell you about the Bruhat graph, which also is mostly a matter of just setting up a little bit of notation. So a reduced word for W is just an expression for W of minimum length in my distinguished generating set S. The length of W is denoted L. I'll write capital T for the set of conjugates of simple reflections. So this is the set of all reflections in W. And for U and V in W, I'll write U with an arrow decorated T to V if U and V differ by left multiplication by this reflection T, and V is longer than U. So this determines the Bruhat graph on W, which is some directed graph, vertex set W, and edges corresponding to these reflections. So, for example, for S3, this is what the picture looks like. All right, hopefully clear so far. Bruhat order is just the partial order given by the transitive closure of this acyclic digraph. So it is graded by length, and I'll use less than or equal to for it. So for S3, this is what it looks like. The Bruhat graph did also have this long edge here, but that's not a cover relation in the poset because it is composed of these shorter cover relations. So this is what the picture looks like for S3. Always, if W is finite, there will be a unique maximum element, which is W naught. So in the case of the symmetric group, that's the reversed permutation. For any Coxeter group, there will be a unique minimal element, which is the identity element of that group. And the point I want to be making with S4 on the right side here is just that already for S4, this is quite a complicated poset. And indeed, there are still open problems just about the combinatorics of Bruhat order. So the definition is simple, but it's a rather intricate poset. Okay, so here is the definition of these objects, PUV of Q, these polynomials. So a priori, they will just have integer coefficients. The polynomial is defined to be 0 unless U is less than V in Bruhat order. So going forward, we will almost always be considering U is less than V in Bruhat order, and we're going to try to be understanding these polynomials in terms of the interval in Bruhat order between U and V. PUU is always just 1. There is this degree bound. So the degree bound is strictly less than half of the difference in lengths. And the most interesting case of the recurrence is this last one here. There are these auxiliary R polynomials which show up here, which I haven't defined for you yet. I'll define those on the next slide. But modulo knowing about these R polynomials, everything over here, these are all Kazhdan-Lusztig polynomials for shorter intervals. So inductively, I will be able to compute the right-hand side here. The left-hand side has PUV appearing twice in it, but because of this degree bound and this shift here, the supports of these two terms will not overlap with each other. So if I'm able to compute the right-hand side, then I'll be able to extract what is this polynomial PUV. So in theory, this allows one to compute these polynomials, although it obscures almost everything about them that makes them interesting. In particular, it is far from obvious from this that they will have non-negative coefficients or any of the interpretations that I will mention in a slide or two. So these are polynomials which showed up in that last equation. These are also indexed by pairs of elements in W, also polynomials in a single variable. These will have genuinely positive and negative coefficients. They are also 0 unless U is below V in Bruhat order. They are also 1 if U equals V. But they're a little bit easier to compute. There's just a simple recurrence based on descents of U and V. So a descent just means that when I multiply U on the left by one of my simple generators, the length decreases. So if we're in the symmetric group and we're thinking about adjacent transpositions as our simple generators, then this corresponds to the usual notion of descents of permutations, or actually its inverse, I think, based on Lie conventions. In any case, if S is a descent of both U and V, then the R polynomial for the higher interval is just equal to the R polynomial for the lower interval. If S is a descent of V but not of U, then I have this slightly more interesting recurrence. So it's not completely obvious, but true that this is a well-defined thing. That is, if you take any choice of any sequence of descents, you will end up computing the same polynomial. But that is true. So these were also introduced by Kazhdan and Lustig. Usually, if people say Kazhdan-Lusztig polynomial, they mean the P polynomials, and if they mean these ones, they will specify Kazhdan-Lusztig R polynomial. Okay, questions about the definition so far? So maybe let me tell you some of the reasons people care about these in a little bit more detail and hopefully relevant to the interests of people in the seminar. So if W is the Weil group, say, of a semi-simple Lie group G with Borel subgroup B, okay, I probably don't need to define a Schubert variety, except that maybe some people in the audience would call this an opposite Schubert variety, but in Kazhdan-Lusztig theory, this is what a Schubert variety is. The open Richardson varieties are also important. So they are the intersection of an open Schubert cell and an opposite Schubert cell in G mod B. Okay, a couple of hints of how these polynomials are relevant to the geometry of these varieties. So first, the R polynomials are the finite field point counts of the open Richardson varieties. These Richardson varieties were introduced in the same Kazhdan-Lusztig 79 paper that the other polynomials and much else were introduced. I believe that is where Richardson varieties were first considered, but Richardson thought about them later. And the P polynomials have an interpretation. They are the graded dimension of the local intersection cohomology of a Schubert variety at the torus fixed point U. So PUV is measuring something about how singular XV is at the point U. It's possible to be a bit more explicit about this in finite simply lace type. So if G is type ADE, then Carol Peterson showed that smoothness of Schubert varieties is equivalent to rational smoothness, and rational smoothness is essentially by definition this fact that the Kazhdan-Lusztig polynomial is just one. So yeah, you should think that the XV is smooth at U if and only if this polynomial is one. And if the polynomial is more complicated, then XV is more singular at U. All right, so here is the combinatorial invariance conjecture, which was in my title. So as far as I know, this was independently considered by Lustig and by Dyer. So Lustig circulated this as a conjecture in the early 80s. Like 83 seems to be the most common date I find, but didn't write it down. Dyer in 87 posed this explicitly in his thesis. It says that if I have a pair of elements U and V in one Coxeter group W and another pair in a possibly different Coxeter group W prime, and if the Bruhat intervals, so this is the closed interval in Bruhat order with bottom element U and top element V, if these are isomorphic just as partially ordered sets, forgetting the labels of the vertices by elements, forgetting the labels of the edges by reflections, forgetting even which groups we're in. If they are just isomorphic as posets, then the conjecture is that the polynomials are equal. So I think this is quite surprising. A couple of reasons why it's surprising. I'll go back to the defining recurrences. So in this recurrence, for example, first of all, this cares a lot about descents, which are about simple reflections, whereas Bruhat order itself has cover relations corresponding to any reflection. And in fact, it's not possible if I just hand you an interval in Bruhat order, you cannot detect combinatorially which cover relations must be descents, which are coming, in fact, from simple reflections. So we can't even begin to apply this recursive definition, given only the poset. The second thing is that this step of the recurrence leaves the initial interval we started with. So if I started with the interval from u to v, I'm going to translate both of them down by s, and I'm going to be considering elements outside of my initial interval. So it's also not at all clear from this that the information is sort of contained in the interval we started in. It's also not clear from any of the geometric or representation theoretic interpretations why these seemingly very different, Schubert varieties of different dimensions at different points in different groups should have their singularities be related. Okay, yeah, I was here. So Dyer proved it when the length difference between u and v is at most 4. So essentially, he showed something about the coefficients, at least the leading coefficient and some of the smaller coefficients of the R tilde polynomials, which I'll define on the next slide, which has this effect. I would say the main general class of intervals for which the conjecture is known is that in a series of works by various sets of these authors in the aughts, the conjecture was proven when both u and u prime are the identity elements of their respective groups. There are a few more partial results when both groups are the symmetric group, but still, I would say, wide open for the symmetric group. In finite Coxeter groups, it's possible to do a finite check, which verifies this for all intervals of at most some length in all finite Coxeter groups. And that has been done, as far as feasible by computer, maybe up to lengths 7 or 8, something like that. But still quite open in general. All right, so I mentioned these R tilde polynomials, which Dyer defined. These are just some variable transform of the R polynomials. So they're encoding the same information. They have the benefit that they have non-negative coefficients. And we can equivalently state the combinatorial invariance conjecture for any of these families of posets. So given just the posets, I can go between the R polynomials and the P polynomials, or the P's and the R's, or the R's and the R tildes. So stating the conjecture we can equivalently state the conjecture for the R polynomials or for the R tilde polynomials, for example. Okay, so just examples of what these things look like. If U is covered by V, then the polynomial will always be 1. So it turns out that the P polynomials always have constant term 1, so this is kind of as simple as it can be. So this is saying something about Schubert varieties not having singularities in codimension 2. In fact, they don't have singularities in codimension 4 either. Oh, sorry, I should say they're not rationally smooth. They're not rational. They are rationally smooth in codimension 4. If I have a larger interval, for example, any interval isomorphic to a Boolean lattice will always have also a trivial Kazhdan-Lusztig polynomial. And in fact, if you go through the considerable effort to compute very many of these P polynomials in small symmetric groups, say, you will find that they're very often just 1, although you have to do a fair amount of work to realize that. But the smallest intervals in which they are non-trivial look like this. So this is a foreground. This is the face poset of a square. Its Kazhdan-Lusztig polynomial is 1 plus q. And this interval, for example, is the culprit if you're familiar with the non-smooth Schubert varieties for S4. Both of these have an interval looking like this below V, and so this is sort of explains why they are singular. So here is the first main theorem of the talk. So this, so with Barkley and Lamb, we prove this for arbitrary Coxeter groups. This was proven in 2021 by Patimo in finite type ADE. So it says essentially that the conjecture is true if we just look at the linear coefficient of the p polynomials. So if I have two different intervals in potentially different Coxeter groups, which are isomorphic as posets, then the linear coefficients of those polynomials are equal. So this square brackets q is my notation for extracting the that coefficient of the polynomial. All three of these bullet points are essentially equivalent after doing some rearranging of the polynomials. So we also get that the linear terms of the R polynomials and the second highest powers in the R polynomials agree, as well as the second highest term appearing in the R tilde polynomials. So we can fill in a chart for which coefficients of these various families of polynomials are known to be combinatorially invariant. Yeah, so the original Kazhdan-Lusztig 79 paper, all of these terms, all of these polynomials, the constant terms are easy to extract. So R and P will have constant terms 1. It's also true that the R and R tilde polynomials are always monic. So this q to the length term is also combinatorially invariant. So I mentioned Dyer's thesis and his introduction of the R tilde polynomials. So it follows from a formula of Dyer's that I'll give later in terms of interpreting the R tilde polynomials as counting certain increasing paths in the Bruhat graph that you can prove combinatorial invariance for the coefficients of q and q squared of the R tilde polynomial. And then the new results just that appear in the theorem above are the linear coefficient for P or for R and these related higher power coefficients for R or R tilde. Yeah, these ones marked dash are just the coefficient is 0. R tilde has all powers appearing have the same parity as the length. So this coefficient is 0. And these ones are 0 just because P has degree at most half the length. So are there any questions so far about the statement?
So LUV is just length of what? V minus length of
Yeah,
V.
I think I might have used different notation earlier. Yeah, LUV is just length of V minus length of U.
Great, thank you.
What does the top power of the P look like?
So that's actually okay. So people care a lot about this thing. So this when P achieves its maximal possible degree, which it does not always, the coefficient of that, roughly length over 2, but there's a parity thing. The coefficient of that is called mu, and people care a lot about those coefficients because they show up in for example, the Kazhdan-Lusztig cellular representations of the Hecke algebra. Those coefficients are exactly the show up in how the Hecke algebra acts in these representations. They are quite mysterious. It's not known for which pairs U and V that degree is realized, and it's not known what the coefficients are. It was conjectured for a while that in the case of the symmetric group, that coefficient was always 0 or 1, but this was disproven by Greg Warrington. And the smallest example is in like S11 or something terrible. And if you restrict to the problem people actually cared about, where the elements are in the same cell, so that they're actually encoding coefficients in some cellular representation, then the smallest example is in like S15 or something. So they're very subtle things. That's kind of that end is the hard end of the P polynomials to understand, the hardest end. Other questions? Okay, so we haven't, it's not completely obvious based on what I've told you, because the degree bound for the P polynomials says that for a length 6 interval, I am allowed to have a Q squared coefficient, but actually knowing all of these coefficients of all of the subintervals is also enough to prove combinatorial invariance for length 6 and smaller intervals. So we also get this in arbitrary Coxeter groups. Okay, so next I am going to go into some of the ideas in the proof, which includes diamond generating sets, which were introduced by Patimo, which we have sort of been motivated in a new construction using those by thinking about the cluster structure on Richardson's, although we don't actually use that cluster structure itself. And I will also mention some related results relating coefficients of R polynomials and X groups of Verma modules. So that's related to what's called the Gabber-Joseph conjecture, which is false in general, but which we establish a sort of coefficient of. But maybe now is a good time for the little break before I get into those things.
Okay, yeah, let's take a short break, maybe until 5:03,